Hello, here we are once again, the physics video lecture. Physics 4B, video lecture 3. And we've been talking about the ideal gas law. We ended up with a pretty complicated discussion of the distribution of speeds. So actually I'm going to go back to the ideal gas law and try to motivate that whole expression that we had. We'll see how long this takes. This discussion isn't in your text, but it's much better than the one in your text. So we'll go back to the ideal gas law and apply it. So ideal gas law, and we're applying it to the atmosphere. So ideal gas law and the atmosphere. And from there, we'll step by step go into those ideas of a probability distribution. But yeah, back to the ideal gas law. So pressure times volume, number of particles, K Boltzmann, time. So the left side here, actually this entire law is just purely phenomenological. If instead of capital N you have the gas constant and the number of moles. So this was a phenomenological law. We motivated it with our discussion of the gas thermometer, okay? And that's how we even motivated the definition of the absolute temperature scale, Kelvin scale. So what about the atmosphere? What we're going to do is imagine a slab of air. So here we are in the atmosphere. We have the y-axis with the ground down here somewhere, and we consider a slab of air. So just some flat volume element of air, and it has a height, dy. It's going to be infinitesimal. And then it's got an area, okay, top and bottom. And we asked what are the forces acting on this. And so the air contains n molecules. So we have n times m times g weight, okay? On the other hand, there's also pressure times area. Pushing up and pushing down on it is pressure plus d pressure times the area as well. So these three force vectors add up to 0 because we're thinking we have atmosphere, we have equilibrium. So that's our free body diagram, right? Free body diagram, force down, force up, force down, imagine a little slab of air. Let's see what happens. We have P times A minus P plus dP times A. Yes, remember the minus sign, the direction pointing down, minus n times m times g is equal to 0 for all the particles of air in there. Maybe I should have drawn some particles. Oh, wait. We'll do it. Because we are assuming gas particles. So inside here, there are all these particles of air. Okay. Okay, so P times A minus P times A, that's going to be 0. We'll have dP times A. Bring this over to the other side. We'll have dP times A is equal to minus, so minus mg. So now what we're going to do is take the n out of the ideal gas law. and substitute that in there. So dP times A is going to be equal to minus, and now the N is PV over K Boltzmann T, P volume, K Boltzmann temperature, and we've got the mg here still. So let's just do a little bit of algebra on this thing. We're going to have dP divided by P, got a minus sign, and now what's going to be left, we're going to divide V over A. So V over A, considering this little box here, is going to be dy, right? Volume over area is going to be a length, that's going to be the dy. So we got a minus dy, and that's the V over A, and P we've already divided through, so we're just mg over K Boltzmann temperature. So this is a differential equation that we can very easily integrate up. So that's what we'll do next. Okay. So what we have done is apply, idea of a little thin slab of gas particles in equilibrium with gravity, under the influence of gravity, and then we substitute that N with the ideal gas law. So let's go ahead and integrate this up. So next, we integrate dP over P from P0 to P, so we put a little prime here, integration variable on both of those, and then we've got minus mg over K Boltzmann temperature. I got to say something about that. Integral dy prime 0 to y. So that's how we've set this thing up to actually integrate it. I do have to make a note about pulling out this temperature. I'm treating the temperature as a constant. So what we're going to have here is a bit of an approximation, but because we're on the Kelvin scale, the decrease in temperature as we increase in elevation is not that much. It's pretty small. It's a couple degrees per 100 meters, or even less than that. And since the Kelvin scale, we're up at around 273 at 0 degrees. So I'm just going to write here, note T approximately constant, not exactly constant. Okay, the results we'll get are certainly good up for a few thousand meters, no problem. Okay, but yeah, just so we make note of that, because in fact, as you go up in elevation and altitude, the temperature does decrease. But again, since we're on the Kelvin scale, it's a couple of degrees versus a couple hundred degrees. Good, so let's go ahead and integrate this. We've got the natural log of P over P0 on the left side. We've just got mgy over K Boltzmann temperature with a minus sign on the right. And if we now take the exponential function of both sides, we'll get P over P0, e to the minus mgy over K Boltzmann T, cross multiply over, and we have, I'll put this in a box, we end up with P is equal to P0, e to the minus mgy over K Boltzmann T. So that's the argument of the exponent. And we could even graph this right underneath as a function of y. And it decreases exponentially. Good, yeah, let's go ahead and showcase that result. So this is called the exponential atmosphere. The pressure decreases exponentially. This is good up to several thousand meters. And we have to now transform it to the statistical idea. We're going to go back to the idea that we have gas particles. Okay, so that's our next step. Namely, what we have is the pressure is decreasing with altitude, the density is also decreasing, and the number of particles per unit volume is also decreasing. So that's what we're going to do next. So again, we're making use of the fact that temperature is almost constant. So since P equal to Nk Boltzmann T over V, go ahead and put that in parentheses, and T is approximately constant for our discussion, we can say that pressure is proportional to this N over V, which is a number density, number per volume. So we can say that pressure is proportional to N, let's go ahead and write it this way. Pressure is proportional to N over V, and we're going to define that as N sub V, the number density. So yeah, we'll just rewrite this thing. So now what we have is N of Y, number density, with or without that little V there, refers to volume, not speed. So N sub Y is equal to N0 e to the minus mgy over K Boltzmann temperature. Of course, with the same graph, this exponential decrease that I had just mentioned. Okay, let's see where that puts us here. So actually, this is worth a little more of a discussion, because, so let's just put N of Y here. You know, we could think of this M just one species of particle. Remember that air has different types of particles in it, different types of gas particles. You're getting partial pressures from all of them. And what you can see here, since we're just talking about one type of mass, is that the more massive particles, the more massive the particle is, the faster this function decays, right? Because it's e to the minus something. So if you had a lighter species of particle that could decay like this, the more massive one would be decaying like that. So more massive or more massive, and this one's less massive particle. And what that means is that the more massive particles will be concentrated at the lower altitudes compared to the lighter particles. Okay. So the trace gases, will be distributed differently according to this distribution here. Good, so there's our exponential atmosphere in terms of number density. So since we have a number density, we can start talking probabilities. So let's see. Number density can be proportional to a probability. Proportional to probability of finding particles at a certain elevation. Particles at y, at elevation y. And since we can interpret that as being proportional to a probability distribution, we can ask what is the average elevation. Okay. So let's go ahead and do that. This one I'm going to assign to you guys. So example And I'll write it out and I'll call this homework. So you can do it on your homework and turn it in that way, but if you leave space in your notes, you can also fill it in there, which might not be bad. So here's what we're going to do. Average value of y. So y average is going to be the integral of y times n of y dy from 0 to infinity, normalized by the total n of y dy, since we didn't normalize n of y to anything in particular. Okay? So this is an average value, and in fact, you see the definition very nicely here in the numerator. This is just normalization. Numerator, it's just that value times its distribution, dy, from 0 to infinity, because our elevations were going from 0 to infinity. So here's what you do. Go ahead and do both of these integrals. There's n of y. This is y times n of y. This is n of y itself, dy. So you just do both of these integrals, and you find out that it's equal to k Boltzmann t divided by m times g. So that's an interesting result. Okay, you do that integral, or you do both of those integrals. One of them needs integration by parts. This one you just do directly. K Boltzmann t over mg when you divide the one by the other. So let's look at what that means. Okay, we'll leave that up. Okay, so what does this mean? Note that we have mgy average, just from this here, is equal to k Boltzmann temperature. So we had something similar the other day. Remember, this is a measure of thermal energy, but this is here is the average potential energy of the particle in our exponential atmosphere. The average potential energy is just k Boltzmann temperature. Or potential energy average, which is what we could just call this left side, is equal to k Boltzmann temperature. So this is actually a principle of statistical mechanics, that any average energy component is proportional to k Boltzmann temperature in statistical mechanics. So that is going to bring us to the Boltzmann distribution. So let me go ahead and just write this. Average potential energy and we'll just reformulate this thing right here kind of loosely as n is equal to n0, which is just the proportionality constant, e to the minus u over k Boltzmann temperature. So the principle I'm just discussing is that this is general for all energies in statistical mechanics. This will bring us up to what's called the Boltzmann distribution. So next, the Boltzmann distribution. Yeah, I like doing this one because everything's going to follow really organically. We got this thing completely fair and square off of our ideal gas law and our, pressure equation. Newton's law. So the Boltzmann distribution goes like this. N of E, very generally, I'm writing N0 or just a proportionality constant. I'm using N0, but just a proportionality constant. Exponential minus E over K Boltzmann temperature. Okay. This is the really fundamental statistical distribution. Okay. And you see, we came up to something very similar to it. This was just one example that we took out of, we had the atmosphere, we had Newton's law, we had the ideal gas law. So it has this very same form. It generalizes to be true of all energy. And in that sense, it's also true for kinetic energy. So true for potential here, true for kinetic energy here. Yeah. So what about kinetic energy of ideal gas particles? So yeah, we have to understand that that generalizes. Yeah, and actually let me go ahead and say something about this. Boltzmann distribution, collection of particles in thermodynamic equilibrium. So for a collection of particles, just so that's been mentioned, particles in thermodynamic equilibrium. Good. There's our Boltzmann distribution. Now, how do we get from this to that very complicated expression I had up on the board the other day? Because here we haven't really skipped a step, made it to here, we're going to generalize it to all energies. The thermodynamic equilibrium was here as well. And I should say something even, if it's true for all energies, then you would have kinetic plus potential, okay? But the potential, in the case of this, because of the property of the exponential function, would just factor off as a product, right? E to the, E to the kinetic plus potential equals E to the kinetic, E to the potential, and you would just factor off the one you'd still have the kinetic to deal with. Okay, so what we're going to do now is deal with the kinetic and not worry about the potential. And in fact, in an ideal gas that's at a constant elevation, we're not dealing with the potential. This thing here came from moving up and down in the atmosphere. Good. So what we want to do is convert this to the distribution we had last time, and that's actually pretty quickly done. I'll just sketch it for you and send this up. So yeah, now we're looking for number, probability of finding particles, between, in a certain energy range. Okay, so we're going to write that down. So they're called the probability distribution of kinetic energy. Probability distribution of kinetic energy. And so let's just write that down in this same form here. So we're going to have dP Yes. So P is for probability defined in a certain increment V. This would actually be kind of a vector now, or a volume box. But we're just going to have a constant here, just some constant again. And we've got this exponential. So since we're talking about kinetic energy, we'd have e to the minus 1/2 m Vx squared plus Vy squared plus Vz squared. And that will be divided by K Boltzmann temperature. That's the same thing I'm talking, right? That's what I have up here. Okay. E to the minus energy, this time it's kinetic energy. And what we have to do is transform to spherical polar coordinates. So this has directional information. If we just want speed, if speeds is what we're interested in, then transform to spherical polar coordinates. Transform to spherical polar coordinates and integrate over all angles. Integrate over all angles, and what we get is now dp sub v speed, and this one I'm going to write down. We get m over here, 2 pi K Boltzmann temperature to the 3/2 power e to the minus m v squared over 2 K Boltzmann temperature. Right, this v squared is this Vx squared, Vy squared plus Vz squared. The transformation to polar coordinates gives you, oh, I left something off here. Yeah. So here we had dVx, dVy, dVz. Okay. Because now we're transforming to spherical polar coordinates, we'll have v squared. The integration over the angles gives us 4 pi. And then this is dv here. And now d goes from 0 to infinity. So this is essentially what we had in the last lecture, f of v, when you deal with the pi and pi to the 3/2 down here. You'll see it comes out exactly. Yeah, and this is therefore the Maxwell-Boltzmann distribution of speeds. And this was the function that we discussed last time, where it's v squared, and then the peak, and then the exponential decay. So it comes right out of this, okay? And we got the same form of the Boltzmann distribution already with our exponential atmospheric distribution right here, where that was the potential energy. Okay, good. Felt like I owed that. Yeah, some of this pretty sophisticated stuff comes right at the beginning of the semester. Don't worry, we got all kinds of great stuff coming up that isn't as mathematically challenging as this. You know, if you want, okay, I'm not going to assign this, but if you went through with all of this and did the integrations, you might enjoy it. Okay. We'd have a pretty complete discussion now of these aspects of the ideal gas. Good. I'm going to consult the clock here. Okay, perfect. So now we're moving into a new chapter, and we're trying to make it through to calorimetry today. So I'll erase these boards and then we'll move on. Thermal energy, calorimetry, topics like that. Yeah, I'm also going to describe some demonstrations to you guys. You can do them as a project at home. And if you succeed, you can take a picture of it and send it along with your notes. Okay, so now we're in the next chapter. We're going to talk about thermal energy. And I'm going to introduce it a little differently. So let's see, we got this out of the way. And yeah, heat and the first law of thermodynamics, that would be chapter 18. But I'm not taking all these things in order, regardless. There we go. Good. Okay, so heat and the so let's just call this thermal energy, chapter 18. Thermal energy. I'm going to start out with the discussion of the demonstrations that you can do. You can work this out at home. So we have the idea of the thermometer that we've already talked about. So there's our thermometer, degrees Celsius. We can even up to there, okay? So we have a thermometer and a fluid. And one thing we can do is put this thing on a stand and put a candle underneath. Now I'm going to make this candle square for a reason. There's the candle, there's the flame. And of course what's going to happen is we can heat the water in the beaker, right, by burning that candle there. So we raise the temperature of water with the candle. And we have a definition of thermal energy just based on this type of experiment, and that is the calorie. And I'm going to write it with a capital C equals, I'm just going to call it the heat to raise the temperature of 1 kilogram of water by 1 degree Celsius. Raises the temperature of 1 kilogram of water by 1 degree Celsius. That's what a calorie is. Lowercase c calorie, ditto everything here, 1 gram of water by 1 degree Celsius. Okay. Now interestingly, this uppercase c calorie is the food calorie. Okay. So uppercase C is our food calorie. And in fact, the way the caloric content of food is determined is by burning it and seeing, you know, the temperature of some substance, say water, be increased. So that's our food calorie. And I'll also block off a little space here. So we have heats of combustion. And since we're talking about food, we could say, you know, fat has 9 calories per gram. And this is the kind of thing you can read on a food label somewhere. And protein and carbohydrate has 4 calories per gram. And alcohol has 7 calories per gram, roughly. And of course, then oil and gasoline and wood and what have you, they all have a certain amount of heat of combustion. And the significance of this square candle down here is that it's a butter candle. And I often show that to some of my other classes, but I didn't bring any butter to work today, so. But that's a project for you guys to do. And let me just describe how you do this. This is voluntary homework. Let's see how many people do it. This is a butter candle. And what you do is you take a stick of butter and in fact, a stick of butter, quarter pound of butter will have 800 calories, right? That's what the label will tell you. So what you do is you take that stick of butter and you press some cotton string through it. Can't be nylon because it'll just burn like that. You have to have some cotton string for a wick. Cotton string for a wick. Okay, it has to be cotton. I'll triple underline that. You press it in there and trim it and press it into the center of the butter there, soft enough to press in. And then you burn it and you'll get a flame. And then this would actually be the demonstration of how you would tell the calories in the butter. The flame would heat the water and would change the temperature of the water. The thermometer would tell you how much, and then you could apply this definition here. Okay, so that's in place of the actual demonstration. But if anyone is able to do this, you know, you got the string and the butter, maybe cotton yarn would work, but it's got to be cotton. Then if you can do this and get a good one burning, go ahead and take a picture of it and send it with your notes. That'll be fun, okay? Good, so that's our discussion of this thermal energy. Now, the calorie is an older fashioned unit of energy, but since it's tied to these things, it's definitely good to know. Anything that will allow you to raise the temperature of that water, right, will be heat. And in particular, you can raise the temperature of water through friction, just like you can raise the temperature of your hands by rubbing them together. If you were to churn that water with a propeller or something, you'd be doing work on it, work measured in joules, and you would raise the temperature of it as well. So that brings us to the mechanical equivalent of heat. Okay. In other words, you can turn work on something into an increase in temperature, which means that you've got some heat going on there. So mechanical equivalent of heat. And the joule churn, this is something for you guys to look up and see if you can get a better picture of it than I can draw. The idea is that you've got here's a crank, a handle, you can turn this churn, and you've got some kind of thing inside that as you turn it, encounters a lot of resistance. So you have to do a lot of work to churn the water, and temperature of the water increases. So you're doing work and increasing the temperature of water. Okay, this is a really important concept, by the way. So the mechanical equivalent of heat is what you discover that 1 calorie of the 1,000. Yeah. By the way, this is called a kilocalorie. This lowercase one is just a calorie. Okay. So one of these food calories, 4,186 joules. That's quite a bit, actually. 4,186 joules. How much mechanical work is 4,186 joules? Okay. After all, we eat a couple thousand of these every day. So how much mechanical work is 4,186 joules? A good basic way to think about this is the stair climb. So you climb a flight of stairs, and let's say it's a 5-meter flight of stairs, and you have a mass of 80 kilograms, okay, then the work is mgh. So I've got my 80 kilograms by roughly 10 meters per second squared for G, and my 5 meters, and that's 4,000 joules. So you can relate all of these things. If you were to slide down a slide of 5 meters, okay, you slide down a slide, then the friction would warm up the seat of your pants by, you know, conceivably by 1 calorie. Okay, this many joules would be converted to friction converted to heat. So let's also point this thing here. What we can say is we have work, friction converted to heat, thermal energy. So this direction of the arrow is also important. Later on in the semester, a couple of weeks, we're going to ask ourselves, hey, what about taking thermal energy and turning it into work? Okay, that'll be a heat engine. But for now, we're just doing work, and via friction, we're producing thermal energy. So the direction of this arrow is important right now. Work to thermal energy. Okay, that sets the stage for calorimetry. I'm going to consult the clock again here. Okay. Looks like the battery on my camera is running low, so we'll see what happens. So we want to make it to calorimetry. And we need the specific heat capacity. That follows right out of what we've done now. Once we have the mechanical equivalent of heat, we don't have to talk about calories anymore. We can just do everything in terms of joules. So that's what we'll do to wrap this up here. Okay, let's see, specific heat capacity. That's what we'll end with. So the idea here is that, just as in our picture, we heated something up with the candle and the temperature increased, we can now just say that if we apply some heat to something, so this is going to be heat, depending on the mass and this material property, we're going to get a change in temperature. So this is mass, this is heat in joules, this is specific heat, or specific heat capacity, and this, of course, is the change in temperature. So we could say if the energy flows into something, it's going to raise the temperature, and if the energy flows out, it's going to decrease the temperature. So we can even have a plus and minus sign here, depending upon whether the temperature increases or decreases. Now, by our definition of the calorie, we have one thing here for free, specific heat capacity. First of all, let's put the, whenever we get a new quantity, we always want to get the units of it, and of course that's the square brackets around that quantity. And you can easily see, we're just going to solve for C here. We have the units joules, mass in kilograms, so we divide by mass, joules per kilogram, degree Celsius. Okay, so those are the units of the specific heat capacity. Now, by our definition, if we have 1 kilogram of water and 1 degree Celsius increase, that's going to be 1 calorie, which is 4,186 joules. So immediately we know specific heat of water equals 4,186 joules per kilogram degree Celsius. The other ones you can look up. So I happen to know that ice is 2,090. So liquid water and ice have very different specific heat capacity. That's interesting. There must be some structural difference between a liquid and a solid, right? And I think copper is 800, but I'm not sure. So I'll put question mark here, kilogram degrees Celsius. But yeah, you get a whole list of them. You go down the list of metals, actually, specific heat of lead is like only a 1 or 200, so very small compared to the specific heat of water, which is pretty much the champion in that regime. Okay, you know what? I'm going to call it a day right here. And the homework for this, I haven't really covered all of the material to do the homework problem out of the book. Now, I already gave one, those integrals, so you can definitely do those. But just looking at the calorimetry section in our book, there's one that we can do just with what we've learned here. So this will be chapter 18. It's not yet a calorimetry problem, really. Okay, so it's really just using the definitions I have up here. Problem 35. Chapter 18, problem 35. And maybe there's another one like that. The other ones need a little bit more than we've talked about so far. Actually, you know what? Problem 49 is talking about friction and heat too. It's under first law of thermodynamics. We don't need that. So problem 49 is good too. 35 and 49. In fact, these are pretty interesting problems. Okay, so next time we're going to continue on with calorimetry proper, and we have to talk about latent heats before we get into the whole thing. Good, so there's enough for you to do now, and see you guys next time.